Hi everybody, welcome to the sessions of chemistry exam. Today we're gonna solve some multiple choice questions. Let's get into this. The first one, the question says lithium with E0 minus 3 volts and beryllium with E0 minus 2 volts are introduced into a voltaic cell. How much is the difference equal to tension at the end? We know that like E0 of a cell would be that E0 of a reduction of cathode minus the E0 of reduction of anode. So the most important thing in this question is to understand which one is like cathode and which one is anode. Okay, since we have like a voltaic cell and the E0 is given by reduction, we know that like E0, which is like less, it acts as an anode, like minus 3 volt we have here and minus 2 volt we have as here. Like for example, lithium in the reduction table would come beneath the beryllium. Therefore, the lithium would act as anode and beryllium would act as cathode. Therefore, the E reduction of cathode would be minus 2 volt minus E reduction of anode, which is the reduction of lithium, would be minus 2 minus 3 would be 1. The question is like, the answer is 1 volt. The next question is kind of important. It says that given this reaction, which is at equilibrium, and the phases are like gases. Given this reaction at equilibrium, 3 moles of gas A, 2 moles of B, and 1 mole of C, and the reaction pressure is 2 atmosphere. It wants the constant of pressure for equilibrium. We know that to calculate the Kp, we need the partial pressure of the gases at the equilibrium state. We have the moles of gases, but we need to somehow find a way to convert these moles into the partial pressure, because we know that in the formula of constant of pressure, we need the partial pressure of the products to the coefficient to the power of coefficient over the partial pressure of reactants to the power of their coefficient. So if we want to write K of P, the formula would be partial pressure of C to the power of 3, like this, over the partial pressure of gas A to the power of 2 times partial pressure of gas B to the power of 1. Therefore, in order for us to have this equation, we need to find these unknowns. And we need to like take a review of the partial pressure formula. Partial pressure of a generic gas M would be the mole fraction of M times the total pressure. And here we are introduced to the total pressure of 2 atmosphere. Therefore, we need to just find the mole fraction for each of the gases. We have A, B, and C, and we have 3 moles of A, 2 moles of B, and 1 mole of C. So in total, we have 6 moles. Therefore, X of A would be 3 over 6, X of B would be 2 over 6, and X of C would be 1 over 6. This is the mole fraction of the gases. In order to have the partial pressure, we just have to multiply by the total pressure. So P of A would be 3 over 6 times 2. It gives us 1 atmosphere. And also P of B, the same thing. P of C, the same thing. Now that we have the partial pressure, we can just substitute them in the Kp formula, and we would get the answer 1 over 18. So this question is important in a matter of finding the partial pressure, and as mole, and it is by the definition is the mole fraction of the gas times the total pressure. So it would be a good review to know this. Next question is actually a very easy question. It says, what is the structural formula of fluorine gas? We know that fluorine gas is like F2, and we know it comes from the group 17, and we know group 17 would have like 7 electrons in their, if in the release structure, we would have 7 electrons around F. So it would be like 1, 2, 3, 4, 5, 6, 7, and another F would be 1, 2, 3, 4, 5, 6, 7. So the covalent bond would be this guy. So this is the structure formula. And this goes same for all the guys in the group 17, like F2, Cl2 would look the same. So basically, this goes for all that group, the bonds. Okay, next one is kind of easy but important in a matter of understanding the ions. So the electronic configuration for sulfide ions. Let's go for sulfur first of all. We know that sulfur is S16, right? Let's start by the atom and feel all the electron levels, like starting from the inner ones, which is 1s2. So we know that it is 1s2, we fill it with 2 electrons, and then we go to the next level, which is 2s2, 2p6. And 2s2, 2p6, it's all full. Until here we have like 10 electrons, but sulfur has 6. So we have 6 more places to be full. Then we go to 3s2, okay? We just left with 4 and we put it 3p4. So this is the electron configuration of sulfur. But for the electron configuration of sulfide ion, we know that sulfur is like from the group 16, and the ion of group 16 would look like something x to the 2 minus the ion. And for example, S2 minus sulfide oxide, O2 minus, and this 2 minus means like receiving 2 more extra electron in order to achieve the electron configuration of the gases. For example, here is argon 18 of the same row. Here we just receive 2 more electrons. 2 minus means 2 more electrons. And the important thing here is that where do we insert this 2 more electron? The important thing is that we insert it from the most outer part. So the 2 more electrons would go and actually sit in 3p6. So this would be the electron configuration of the sulfide ion. Okay, the next question is kind of important. It's asking for Van Hoff coefficient of sucrose. Sucrose is kind of like glucose, is kind of molecular, and this is like the formula, the molecule formula. Important things here is like, okay, we know this is like the formula for Van Hoff coefficient. It's like I1 plus alpha being the degree of dissociation times n minus 1. And n would be the number of particles after the whole dissociation process. So we know this formula. And here, alpha, in order to understand alpha, we have to think about how sucrose actually, what happens, does it dissociate, what happens to sucrose, for example, when we put it in water. The important is like sucrose will dissolve in water, but it won't make any ions. Like for example, if you have NaCl, like sodium chloride, if you put it like into water, you would have like, for each mole of it, we would have like Na plus Cl minus, the ions. But for molecule like sucrose, like glucose, they won't dissociate and they won't like make ions. They would dissolve in water in a molecular way. For example, mostly using hydrogen bonding. So they won't make any ions. Therefore, they would not make any ions, and the degree of dissociation, which is like related to because sucrose, the same as glucose, these guys solve in water in a molecular form. They won't make any ion. They would just make, like, for example, hydrogen bonding. They would solve in the form they are by making the intermolecular forces. For example, for this guy, it would be hydrogen bonding. So alpha would be 0. This would make this alpha 0, 0, this whole thing, and the I would be 1. So the Van Hoff coefficient would be 1. It wants the name of this guy. This is basically so simple. We know that this is like our metal, and so it's called sodium. We just put it as sodium, and this is like Na, and we know that this is the ion OH minus, and it is called hydroxide. So it would be sodium hydroxide. As simple as it can get, like this question. Okay, next one is asking which group is ethylene part of. The important thing about like hydrocarbons is like there are some groups that we must know, like they're important. For example, alkanes, just for a review, we know that there are like CnH2n plus 2, and then there are like alkenes. These guys like we have alkenes, which is like CnH2n, that they have double bonds, and then we have alkynes, which are CnH2n minus 2, and they have the triple bondings. And by this part of the naming, you can understand this is like ethylene, so it would be like a ethylene or ethene, so it would have like a double bonds, and it would be a part of alkenes group. Number 8, it says indicate from left to right the oxidation number of chlorine in the following ions. We know that oxidation number, we know the whole process, but let's go from left to right. We have ClO4 minus, okay? We want to know the oxidation number of Cl. This one is our unknown, the oxidation number. So, for example, let's decide as if it is X. And we know that the whole of this structure would equals to -1 because of this minus. So there it would be X, and we know the oxidation number of oxygen mostly in most of the most of the forms that we can see, the oxidation number of oxygen is -2. Sometimes it could be +2 even, but mostly for Cl is one of those things which gives -2. But for example, when it comes with F, it could actually be positive, but here there is no F here, so it's just Cl, and it's the usual case of -2. So it would be, we take this as X plus 4 times -2, which equals to -1, this guy. So therefore X would be 7. And then colorate anions, which is ClO3 minus, we do the same thing. Like here we take this as X plus 3 minus 2 minus 1, which give us X equals to +5. And we do this for this two other guy. So it would be 7, 5, 3, 1, this question. And sometimes for some of you guys which are like too much interested in chemistry, we know that the oxidation numbers of Cl actually is a very popular one. 7, 5, 3, 1 is actually a popular one. So you can just go by heart, 7, 5, 3, 1. But either way, you can just calculate it this way. Okay. How can the equilibrium constant vary? Okay. The equilibrium constant, which we mostly introduce as K in most of the cases, there is a very important point about this K. Okay. Nothing can affect this K for a certain equation, for a certain equation. It won't ever change unless you change the temperature. So the constant equilibrium depends only on the temperature. So if you add a catalyst, or changing the concentration, nothing. Like for a certain reaction, the constant of equilibrium only depends on the temperature. The only way that you can change the constant of equilibrium would be by changing the temperature. Otherwise, you're not able to change this constant of equilibrium. So it's a very good point here for you to review this. The constant of equilibrium depends only and only on the temperature. So here temperature would be our answer. Okay, next one is asking the density of a gas is. Okay, in general, we know that density is like somehow proportional to the like N over V kind of thing, like mass over volume, something. So it has like proportionality to the moles or to the mass, and like inversely proportional to the volume. But here we are talking about temperature and molar mass. Okay, it could be like directly proportional to molar mass, but here it's written inversely, so that would make no sense. But let's see about the temperature. Here we have volume, so if we want to see how it is affected by temperature, we have to find the relationship between the volume and the temperature, which you can find like in the ideal gas law, sort of. We can go by this logic. So PV equals to nRT, okay? If we keep all these guys constant, we know that by increasing the temperature, we would increase the volume, and also vice versa. By decreasing the temperature, we would decrease the volume. Therefore, so volume is like directly proportional to temperature. So whatever we have like here would happen the same for temperature. So here, like the density is kind of inversely proportional to volume, and therefore we can say inversely proportional to temperature by this logic. Make kind of sense. Because like when you rise the temperature, the volume would increase, and therefore the density would kind of decrease. Kind of make it is like logical in real life as well. Okay, from which of the following mixture does the hydrogen evolve? Okay, we want to see from which of this guy reaction we would like get hydrogen in the product. Okay, as you observe, like we have hydrochloric acid and and like sulfuric acid. So and the other guys like here are metal. So we can go by metal plus hydrochloric acid. And we know that the reaction for metal plus hydrochloric acid would actually evolve hydrogen. But here we have like Zn, Pt, and Ag, all of them are like metals. So why only we are choosing Zn as the one that is producing hydrogen? The reason is that Ag and Pt actually they're not that reactive. So like they only may react in a very like special condition. So here normally we consider them as not non-reactive metals. Therefore we can go by Zn easily. And the sulfuric acid, for the sulfuric acid case, is like, first of all, Cl is just a non-metal, so it doesn't make sense even to be consider this reaction. But like for Cu, if we go, we will get H2O. We would not get H2. So the best option here would be this guy. Okay, next question is very important, and it could be like a more of a physics things, but makes sense here also. In the case in which a reaction occurs at a constant volume. Okay, why this constant volume is important? Let me pause here and like talk about this constant volume first of all. Constant volume actually work is for like a gas kind of thing is kind of proportional to the changes in volume. Mostly it would be an integral form of changes in volume, but let's think of the work is something which is like happens by change in volume. So if we keep the volume constant, it actually means that there is no work involved, okay? So this whole at constant volume can like corresponds to saying like no work. Therefore, let's continue. So until this part, I just paused and I understood, okay, this guy means no work. And constant T, okay? It can be stated that the heat freed or absorbed always to what? So it's talking about work, it's talking about somehow temperature, and it's somehow here in these parts of the answer is talking about internal energy. This is where it hits first law of thermodynamics, like internal energy, heating, and work, where these all guys come together. In the first law of thermodynamics, we say that the changes in the internal energy would correspond to heating or heat plus work, right? And here, since there is like a constant volume, which states that work is 0. So like if there is a heat being freed or absorbed, Q is like the heating. It means like this is the only way of changing the internal energy since work is like equals to 0. This would correspond to the answer A, the best way, the best solution for this. Okay, the next question is kind of like not that hard, is more of like based on theory things. So which of this crystal structure has the largest packing factor? So it's just something you must memorize. And here I brought like a summary of that. Several types of crystal structure, for example, hexagonal, close packed, which like the packing efficiency is like 74%, face center cubic, like the same as this guy, like 74, body centered is like 68, and like this simple cubic, which is 52%. So between these choices, the face centered, which is like 74%, is like the highest one, largest one. It is more of a like a theory question, nothing that complicated, something you should memorize sort of. Okay, the next question has a very important point in it, which actually by understanding it help you understand this whole stoichiometry of gases. So I'm just gonna explain it in a very nice way. Okay, first of all, this is something about the gases, a very beautiful special law about the gases is that if you keep the temperature and pressure constant for a gas and choose any gases regardless of the type of the gas. So I'm just gonna write regardless of the type of the gas. You would have the same volume. For example, let's think of it as like these balloons maybe. So you're introducing a constant temperature. Okay, guys, let's put the room temperature to this constant, and also let's keep the pressure constant, no change in pressure. So I'm taking this constant and I'm taking this constant, okay? Then you choose, for example, 1 mole, this could be like 1 mole, like, or the same amount of moles. Let's say 1 mole of different gases. Like, for example, I put 1 mole of nitrogen here, and then here I put 1 mole of oxygen. Then if you go and see like the volume and calculate the volume, you will see that these two balloons have the same volume. This could be surprising because this guy is nitrogen, this guy is oxygen. So it could be like kind of tricky, but this is a very special case for like ideal gases mostly, that in constant temperature, if you keep the temperature constant, so this constant is actually really important. Constant temperature and constant pressure, volume of 1 mole of all gases, ideal gases, like if I want to be more precise, regardless of the type of the gas, they're all equal. So this is such a cool thing. And to even make it more cool, in constant temperature and constant pressure, let's choose a constant temperature and constant pressure. For example, I'm just gonna choose like 0 degree of Celsius and 1 atmosphere, okay? This is what I'm gonna choose. And then all gases would have the equal volume. And if we measure this volume, it would give us 22.4 liter. This is so cool. This is why this is like an important number in stoichiometry of gases. So for in STP condition, which is this condition that I just said, 0 degree Celsius and 1 atmosphere pressure, this volume, which is equal, this volume is equals to 22.4 liters. So volumes of all gases, regardless of the type of the gas, are like equal. And if we put the temperature and pressure to these numbers, it would be equals to 22.4 liters. Okay, so if we have double of this amount, it means that we have double in the amount of the gases, so 2 moles, right? So 2 moles would be the correct, and then we have to check if it's the STP. if we go through all the options, this guy is like expressing this TP. So this would be the correct answer. But this point is really important. It's in the whole gas stoichiometry. Okay, number 15. How many electrons can occupy the same orbital at the same time? Such a basic question. We know that each orbital can be occupied by 2 electrons, which have like also different orientation. Like this. Very easy one. Like, so this is all of it.